Yes, I do. Okay, good morning, everyone. My name is Cornel, and I'm a PhD candidate at the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany, as well as an instructor at Columbia College in Vancouver, Canada. And I would like to tell you a little bit today about this package that I've been developing called Lithics3D for helping researchers work with virtual representations of archaeological artifacts within the R environment, and more specifically with 3D scans of stone artifacts. So I would like to tell you a little bit about this package, what it can do for you. So I'm going to walk you through some examples, and then I'm also going to tell you a little bit about what I hope the future holds for this package. But before that, just a little bit of background. So many archaeologists have been really excited about working with 3D models for a long time now, and that is because there are several advantages to it. So these models are very easy to share and disseminate. They also capture a lot more information about the variability of an object than traditional caliper measurements, for instance, and that means that they can be repurposed. And finally, with these kind of models, you can also theoretically at least automate the analysis. And automation is really fantastic news, not only for lazy archaeologists, but also for archaeologists who are interested in working with large data sets, and for archaeologists who are interested in having very clear definitions. And what I mean by that is that the process of translating a query such as what is the length of this artifact into something that makes sense to a computer really forces us to be very explicit about what it is exactly that we mean by things such as length. So automation is great, but one of the tasks that that automation requires is to be able to identify components of interest on the surface of these models. And this is a problem that researchers have been working on for quite some time. This here is a figure from a 2001 publication where the authors were advocating one specific method for doing this, for recognizing ventral surfaces, dorsal scars, and whatnot. There has been some progress since then. In 2014, Richardson et al. Published or presented here actually a method that seemed really quite promising. These are the kind of apologies. Uh-oh. Yeah. Okay. These are the kind of results that they were obtaining. Unfortunately, there hasn't been a follow-up to this work as far as I know, at least. In any case, in 2018, Baron et al. Published a way of extracting these kind of outlines, which are basically, they were pursuing automatic artifact illustrations based on these 3D scans. And that also requires us to be able to detect components of interest. But here's the thing, though. It's been 18 years. The progress that has been made really hasn't been quite as substantial as many of us have been hoping. And when I started developing this Lithics3D package, I was also on this quest for full automation. But then I realized along the way that maybe that was being a little bit too ambitious based on the current state of the art. So the current priorities for the Lithics3D package are a little bit more modest. What I aim to do with this package is to reduce the complexity, first of all, of working with this kind of models within the R environment, and to provide a set of functions that are as useful as possible. And what I mean by that is to provide a set of functions that can be reused and recombined in a variety of ways in order to allow researchers to look at these kind of models in a new way, to analyze new characteristics about the artifacts that I cannot envision at the moment. So it's really a toolbox for you. Now, in order to do this, I adopted the landmark-based approach, so a hybrid approach where the package relies on expert input. So human experts are required to place landmarks at the moment. For example, delimiting the platform and around the edges of this flake. And there are several advantages to this approach. First of all, it's reliable because it's supervised by a human expert. It is also fast, and it is also, I think, a step towards full automation, because the idea is to reduce the number of required landmarks and eventually eliminate them altogether. So I'm still very much pursuing that goal. I'm just taking it step by step. And this approach is also useful right now because we can use landmarks in order to identify features of interest, such as a working edge, for instance. We can use those features of interest then to perform measurements such as edge angles and to isolate surfaces. So this is a little bit of what the design philosophy behind Lithics3D is. Now, Lithics3D currently provides functions for working with this kind of virtual models as geometric objects. So functions for basic geometric operations such as intersections between planes, lines, and spheres. Functions for computing angles, volume, surfaces, and also for rotating 3D data in a way that allows us to standardize the orientation of artifacts. It also provides functions for connecting landmarks on the surface of the object, following ridges or valleys, for instance, and to measure things such as edge angles along these paths, and also to segment these objects. So Lithics3D right now is published on GitHub. I plan on submitting it to CRAN in the near future. It's not quite there yet. But it relies heavily on a set of R packages, such as Morpho, iGraph, Geomorph. Yeah, I think that's all I have to say about that. Now, the rest of the presentation, I just want to demonstrate what you can actually do with this package. But before that, I just want to give you a little bit of an idea about how this function for connecting landmarks on the surface actually works, because it's really a critical component of the package at this moment. I'm working on alternatives to this function, but right now this is the function that you want to use. So what this does is it takes this mesh object, it extracts the edges that compose the triangles on the surface of this object, and then on that basis it creates an iGraph object which has weights associated with each edge. And this weight is the reciprocal of the mean curvature of the vertices that define that specific edge. And using the reciprocal means that when you have zones with very high curvature values, you have very low weights, meaning that those edges are very easy to transverse. And when you have very low curvature values, so a flat surface, you will have a very high weights. Essentially, you're penalizing flat surfaces. So anyway, this SPath connect function basically connects landmarks in pairs, landmark 1 to landmark 2, landmark 2 to landmark 3, and so on, and uses this function from the iGraph package in order to compute shortest paths on the surface. So what can you do with this? Well, this is one of the things that you can do. You can perform segmentation. So using these landmarks on the platform and along the edges of this flake, I can go from this to this. And as you see, it works pretty reasonably. So what is required in order to do this? Well, this is the article that is required. So you use this SPath connect function to request that these landmarks be connected following ridges along the platform. So that's what that does, and this will output a list of vertex IDs on the surface of this mesh that must be transversed. Then you have this function, mesh segment by path, which allows you to actually cut the mesh along that path. So that will output isolated surfaces in order of their size. So because this platform component is much smaller than the body of the flake, the platform of the flake will be the second element in this list. And the body will be the first element. Now you can repeat that same process using this landmark, so landmark 1 to landmark 4, then all the way around the edge to landmark 2 and back to landmark 1. Forming a closed path, and then you segment by the mesh by that new path, and voila, you have the dorsal and the ventral surface. And again, this is what the result looks like. Now, you can also use this, of course, to isolate other types of surfaces, such as dorsal scars. So if you provide landmarks to delineate those scars, they can be isolated. This is a very high resolution scan containing about 2.3 million vertices and 4.5 million faces. So in this kind of scan, the protocol works quite well, but it also works quite well on lower resolution scans. So these are from the dataset published by Morales et al. In 2015. There are a couple of gotchas. So if you have meshes that have been simplified and in flat areas you have very large triangles, whereas on ridges you have very small triangles, it doesn't work all that well. So you need to remesh it to a uniform size. There are also another gotcha is that if you have converging ridges such as this one, where one of the ridges has much higher curvature than the other one, then the shortest path function might jump to the other ridge, taking the penalty for crossing flat surfaces. But the solution to that is simply to put more landmarks in those convergence zones. So overall, it works, yeah, pretty well. Now, what else can you do with these paths? Well, one of the things that you can do is you can extract outlines and orient this, and this can be useful if you want to do shape analysis using elliptical Fourier, for example. So I take these landmarks for the platform, then I can extract, again, create a path using the sPathConnect function. What this line does is it simply extracts the coordinates from the mesh object of those vertices along the path. And then I can use this function in order to perform a PCA alignment of this contour and then apply the same transform to the actual mesh object with which it is associated. After that, because these points will be in 3D, I can use this path resample function using only the XY coordinates in order to obtain equidistant points in a closed contour with a known starting point, which in this case would be the point of percussion. So this can be used right away in elliptical Fourier analysis. You can also do this. So if you wanted to investigate the properties of ventral surfaces, for instance, you can request that these landmarks be connected along the edge of this isolated ventral surface. And you can orient this entire mesh just by the contour, like that. And what that will do is it will, so this will be on the same plane, on the XY plane, and you can just simply look at the distance between the vertices of this mesh and the plane on which this contour is found in order to figure out what, for example, the thickness of the bulbal percussion is, or how far it extends on the ventral surface. You can look at other characteristics of the ventral surface with this too. What else can you do? Well, you can also measure edge angles automatically. So having these two landmark points, and I'm only using two landmark points in this case because I want to show you that the sPathConnect function really follows ridges quite nicely. So you can go from this to this with 3 lines of code. So basically what this does, it requests, so I was interested in this case in finding out the angles measured at 5 millimeters inward from the edge at 1 millimeter sampling intervals for a total of 66 angle measurements. Now this again is a very, very high resolution mesh, and this so going from this to this on my Surface Pro tablet takes about 58 seconds. But these parts of this function are cached, so it actually runs faster on subsequent queries. So how does this actually work? Well, again, you connect these landmarks using the sPathConnect function, then you resample the path to equidistant point, but using the distance option so that they are located at a distance of 1 millimeter from each other, and then you just request the angles at a distance of 5 millimeters. This code over here is simply doing this plot, which shows you where exactly things have been measured. Things are messy over here because the edge is messy over there. These calculations are done fully in 3D, so it just follows the contour of the edge. All right, so how is this done internally? Well, for this calculation, you need first of all to compute a path, a plane which is perpendicular to the curve defining the edge. So for that, I have this function which, first of all, okay, so let's say that we want to measure the edge at this point defined along a curve defined by these 5 points. The first thing that it does is it looks for non-collinear points along the edge. Okay, and then then on the basis of this next non-collinear points, it forms a plane that is parallel to the edge. Then the normal of that plane will give us the first auxiliary point. Then I have this very silly but useful function called circle center that assumes that these points are on the circumference of a circle and calculates the center point of that circle. And having those auxiliary points, you can define a plane that is perpendicular to the edge section there. And what you can do afterwards, you can use that plane in order to obtain a slice of the mesh. This is an approximate function, but that will be changed in the near future. But you can use this to calculate the intersection of a sphere of the requested radius, 5 millimeters in this case, and the distance between those intersection points you can just use simple trigonometry in order to calculate the edge angles. All right, what else can you do? Well, you can also orient objects by two vectors. And this might seem like a silly thing to do, but it's actually quite useful because it allows you to orient objects in a standardized way using two main attributes of interest. So what this function does is it simply rotates the object so that the first vector that you input is on the x-axis with the first point having a value of 0, and that the second vector is parallel to this to the xy plane with the first point having the lowest y value. And one of the reasons why this is useful to do is because it can reduce the dimensionality of problems from 3D to 2D. You can orient the artifact in such a way that it really becomes a 2D problem. Okay, and the other thing that you can do with this is that you can align artifacts, as we did in this case, so that the point always points in one direction. So all these artifacts are aligned along their technological axis, but they are also aligned relative to their working edges. Okay, and then based on the standardized orientation, you can examine distribution of thickness, for instance. All right, so I will leave it at that. Now, I'm just going to mention a couple of things about what I expect to do in the short term. So I would like to implement more basic functions that allow you to do whatever you think is cool. I want to finish building a benchmark data set for evaluating automation. So I want to, so I have a large collection of scans which I want to fully analyze and with this package, and to have that as a benchmarking data set against which I can evaluate things that I plan on implementing a little bit later. I also need to improve the documentation of some of the functions, and one of the functions that I want to implement as soon as possible is something to identify the fracture propagation direction on isolated surfaces, such as the ventral, on flakes. And also, medium term, I would like to do partial surface matching, so to develop an algorithm for matching ventral surfaces with dorsal surfaces. I think you all know where that's going. Yeah, and to develop more unsupervised and segmentation and orientation algorithms. Okay, so do I have? Yeah. So in terms of a wish list, I would really like to have something, a facility to do the landmarking within R. Because yes, there are a couple of options, but they really don't work all that well. And it would be very, very nice to be able to do the landmarking in R and be able to connect, to see how those landmarks connect on the surface of the flake live. Unfortunately, that's not there yet. So if anyone wants to implement it, that would be great. Now, other than that, I would just like to thank all the people who have, in various capacities, made the development of this package possible, and also the various institutions. And to thank you for